Hello, I am Hannah, and in this lab I investigated the motion of a mint pushed horizontally off a table. The purpose of this experiment was to compare experimental data with two computational models, a projectile model without air resistance and a projectile model with air resistance or drag. Using Newton's second law, I tested which model better matches the observed trajectory. I found that the no-drag model predicts a larger horizontal distance than observed, while the drag model better matches the experimental data. However, neither model predicts terminal velocity from this shortfall. First, I determined the system to be the mint and the surroundings to be the earth and air. After being pushed, the forces acting on the mint are gravity aiding the fall and drag opposing the motion. Newton's second law states that the acceleration is the net force divided by the mass, so the acceleration is dependent on both these forces. Without the drag, the horizontal velocity has no force acting on it, so it remains constant, and the vertical acceleration is constant at -9 meters per second squared. However, with drag, both the horizontal and vertical acceleration are not constant, as it is dependent on the changing velocity. The initial conditions used in both the experiment and the simulation were a mass of 0.1 kilograms, initial height of 1.269 meters, initial velocity of 1.17 meters per second, initial vertical velocity of 0, and a gravitational acceleration of 9.8 meters per second squared. These values were measured through our experiment and then plugged into the code. I utilized Newton's second law numerically using Python. At each time step I calculated the gravitational force and the drag force and then added them to get the net force. I updated the velocity using acceleration, and then I updated the position using velocity. The simulation route lines in a very small time steps to approximate continuous motion to account for the change in velocity. When drag is set equal to 0, the simulation represents ideal projectile motion. When drag is included, the model becomes more realistic. Here's the trajectory comparison graph. The blue represents experimental data, the orange represents model without drag, and the gray represents model with drag. We observe that the no-drag model predicts the mint travels further horizontally than it actually does. The experimental data shows a slightly steeper downward curve, and when drag is included, the horizontal distance decreases and the model better matches the experimental points. This makes sense because air resistance opposes motion. It reduces horizontal velocity over time, and since horizontal velocity determines range, the mint lands sooner. This demonstrates that even small objects experience a noticeable drag. Terminal velocity occurs when the net force on the falling object becomes 0, meaning the drag force is equal to the gravitational force. When that happens, acceleration becomes 0 and the velocity becomes constant. Looking at the velocity versus time, the no-drag model does not predict terminal velocity. The vertical velocity increases linearly forever because the gravity is constant and not opposed. In theory, the drag model predicts terminal velocity because as the velocity increases, drag increases until it balances gravity. However, in this experiment, the mint only falls 1.3 meters, too small to reach terminal velocity. To measure terminal velocity experimentally, I would drop the mint from a much greater height, such as the tallest stairwell or building, and measure velocity versus time. When the velocity graph levels off and becomes constant, the constant value would be the terminal velocity. If the mint is thrown straight up with the same initial speed of 1.1 meters per second, without drag, the time to reach maximum height is v0 over g. The total time in the air would be 2 v0 over g. In the original experiment, the mint had 0 initial vertical velocity. If thrown upward, the mint first moves upward, stops, and then falls. Therefore, the total time to reach the ground would be longer. With drag included, the time would still be longer than the horizontal launch case, but slightly shorter than the no-drag prediction because drag removes energy from the system. So in both cases, the object thrown upward stays in the air longer than the horizontal push from this height. Possible sources of error include inaccurate measurement of initial velocity, camera frame rate limitations, air currents in the room, assuming linear drag instead of quadratic drag, and small measurement uncertainty in table height. These factors could explain the remaining differences between the model and the experiment. In conclusion, this lab demonstrates how Newton's second law can be used to model projectile motion. The no-drag model overestimates horizontal distance, including air resistance, and proves in agreement with the original data. The mint does not reach terminal velocity during such a shortfall. A taller drop will be required to observe terminal velocity. Overall, the computational model successfully explains the observed motion using fundamental physics principles. Thank you.